Let us first introduce some fundamental concepts having to do with the probability theory. If you have a trial of some sort, you can have a different number of outcomes. For example, if I flip a coin, then the outcomes can be heads or tails. So it can be heads or tails. These we will call outcomes. Or for example, if I throw a die, then they can have 6 different outcomes. So we can have a normal die, 1, 2, 3, 4, 5, or 6. So that is what we call the outcomes. And then we can talk about an outcome space. An outcome space is a set, the set of all outcomes we can have. So here we have H and T. That's a set of H and T. And in this case, we have the outcome space is 1, 2, 3, 4, 5, 6. So these are outcome spaces. So, for example, 1 is an outcome, a possible outcome, and this is set here is the outcome space. And then we can have events. Events could be basically anything. It could be a combination of different outcomes, or it could be something else. For example, in an event could be that 1 or 2 will happen if you throw a die, or that it will rain tomorrow. So these are events. This will be indicated by capital letters. For example, we can call this X, call this Y, or whatever letter we prefer. So these are called events. So events can be combinations of outcomes, or anything that could happen or not to be true or false. If we have another event here, for example, set, let's say 2 or 3 would happen. In this case, X and Z could both happen at the same time. For example, if 2 is, you throw 2 on the die, then both of them are true. But if you throw a 4 on the die, none of them happens. So for events, we can have that 2 or more of them can happen at the same time, or none of them can happen. Per definition, outcomes instead are or covers all possible things that could happen. So we know that one of these will always happen if you have an outcome. And we also know that not 2 of them will happen at the same time. So if one happens, we know with certainty that none of the others can happen. So outcome is a special type of event that there are only one of them can happen, and we know one of them will always happen. So that's the difference between outcome and event. So both are events, but outcome is a special case of an event. Then we will talk about the probability of an event happening, or an event being true or not true. So for example, what is the probability, and that we indicate by a P for probability. What is the probability that event X will happen, or what is the probability that event X is true? By probability we mean the likelihood, how plausible it is that it will happen. So what is the probability that X will be true? And this we give a number between 0 and 1. If it's 0, we are certain that it will not be true. If it's 1, we are certain that X will be true. And in between there's a grayscale. So in the middle, for example, if you have a half, then we know we are equally sure that it will happen as it will not happen. So the higher the probability, the more likely is it that X will be true, or that X will happen. So, for example, assume that we have a tack and we have thrown it many times. So we can have 2 outcomes here. We can have pin up, or we can have pin down. So if you have thrown the pin or the tack a number of times, we can have these 2 outcomes. So let's call this outcome for 0 and this for 1. So what is the probability that if we throw the tack once, that we will have an outcome 0? if this probability is, for example, 0.4, then we are a little bit more likely that we will have a pin down than a pin up. So this means that it's more probable that we will have an outcome 1 than an outcome 0. But how could we figure out this probability? Let's say we repeat this experiment many times. We throw a lot of pins. So let's say that we get frequencies or relative frequencies. So we throw this pin a lot of times, several times. Then we get pin up. Well, let's for a moment do it like this because it's more clear. How many times did we get pin up? Or what is the relative frequency of that? Let's say we got this 43%. And then, of course, the pin down will be the remaining. So the relative frequency of pin down will be 57%. So 40% of the outcomes will be pin up and 55% of the outcomes will be pin down. If we now have thrown the pin a lot of times, several times, in theory, like ideally in the limit, infinitely many times, but of course in practice we can't throw it that many times. This will be an estimate of the probability, a good estimate of the probability. So we can say that the probability then, if we are thrown a lot of times, will be something close to 43% of getting pin up, and the probability will be close to 57%. So that is, we define probability in terms of relative frequency. So the probability for having pin up is equal to the relative frequency of having pin up. And the same thing for pin down. And this is if we have repeated. If I have done the experiment, or experimental, from the pin, that is, infinitely many times. Many times. Or in practice, a lot of times. For example, whatever, say we've thrown it millions of times. Then we expect this to be the case. And more generally, the probability of an event is equal to the relative frequency of that event happening. So if you want to find out or test, check the probability of an event, we have to repeat the event a lot of times, infinitely many times. And then the relative frequency will be the same as the probability. And relative frequency is always something between 0 and 100%, or a number between 0 and 1, and therefore also the probability will be that. In some situations you cannot, of course, repeat an experiment. For example, what is the probability that the internet will collapse year 2000? Now we are already past 2000, but before year 2000 this was a real problem. But of course, how can you repeat an event like that? You can't really. So then in this case you have to reason in some way. You have to think of like a parallel universes, or you have to think of an ideal experiment. So you can also do it some other way. But for the most cases, we will think about this where you can think about an ideal experiment. Either you can perform it in reality, or you can have as a thought experiment. Okay, so we have that the probability for an event is equal to the relative frequency of event if you have repeated infinitely many times. And the relative frequency is, of course, the frequency of that event. That is how many times X has happened, divided by the total number of times we have thrown from our die or a repeated experiment. So then this means that if n goes to infinity, we have thrown a die or a repeated experiment infinitely many times. And then let's say now, for example, that let's make a graph. And let's put relative frequency here. And then we put n here, the number of times we repeated experiment. And let's now take again with the example with the pin. So we have thrown it a lot of times. So let's say we've thrown it 10 times, and then 100, 1,000, 10,000, and so on. Okay, and then on this axis we have the relative frequency. So we have a number between 0 and 1. If we throw the tack now 10 times, we could basically have any outcome. But let's say we got an here. If you throw 100 times, let's say we got in this. So 45 or 47% of the cases. 1,000 times, then maybe we have gotten here. And 10,000 maybe gotten here. And 100,000. So after a while you can see that this will start to stabilize. Or it should be horizontal here. This will stabilize at some value. Okay, so if you have, let's connect these here also. So we connect our data points. So in this case, we see that the relative frequency will start to stabilize at some limit. And let's say here that this limit is 0.47 or whatever. Then we have an estimation of our probability. So the probability of having this pin up, we estimate it at 47%. And that's since it stabilizes like this. So if we repeat an experiment in the beginning, of course, it can fluctuate wildly, but if you do it more and more times, it starts to stabilize at this limit, which is the probability of the event will happen. So that is yet another example of this. Then, of course, one can ask oneself, let's say that if we throw the pin 1,000 times, how many times would we expect to get a pin up? Then let's use this up here. You see that we can write f of x, the frequency of x, the number of times x will happen. That will be basically, if you multiply up n, the number of times we throw the pin, times the probability for that to happen. So how many times do we will get pin up? And we can estimate it at 1,000 times the probability. And we now know that the probability is 0.47. So 470 times we would expect it to happen. Of course, in reality, it will probably not happen exactly 470, but something close to that. So 480 or 490 or 450, something like that. That will be the most probable will happen. So we can estimate how many times we will get an outcome. Or let's say here that I have some strange looking rock with flat surfaces. So it could be any shape. So it looks like some kind of die, but it's not symmetric for the sides. So let's say I put the 1 here, for example, and 2 here, and 3, and so on. What would be then the probability for example, 1 to happen? Then of course I can repeat. I can throw this rock infinitely many times, or in practice a lot of times, so thousands of times. So the probability of having this outcome 1 will be given by this. So the frequency of getting that in an experiment, and this is how many times I've thrown it. Of course it will not be exactly, but we estimate it at that. So let's say I've thrown it now 1 million times. And let's say I have gotten, how many ones have I gotten? Let's say I have gotten that 200, let's say I've gotten 200 times, 200,000 times. Of course, it's very unlikely to get exactly 200,000, but let's say something roughly to that. Then we can shorten here, and then we have 2 tenths, so 20%. So in this case, I would estimate the probability of getting a outcome 1 as 20%. So this is how I can estimate the probability. A good tool to use when you're doing probability theory, calculating with probabilities, is a Venn diagram. And Venn, that's the last name of a person. So Venn diagram, what is a Venn diagram? That's a way of representing probabilities with a figure. For example, let's say we have an example like this. This here now, the rectangle, corresponds to, inside this rectangle is everything that could happen. So you can have any event that could happen, we have inside there. So let's say that if we're throwing a die, then we can get 6 outcomes. Let's just put the dots here in no certain order. So you can get the 1, 2, 3, 4, 5. And let's put actually the last one inside the circle, for reasons I will come back to. 6. So I just put them randomly inside the rectangle here. So this is everything that could happen. We can have 1, 2, 3, 4, 5, 6 in a normal die. So this is the outcome space of we have thrown a normal die. Okay, then what does this circle here represent? This represents an event. So in this case, X represents the event that 3 or 6 will happen. So this is the event, 3 or 6 will happen. Instead of writing or, one can also write mathematically, symbolically as U. 6UX, and this stands for union. So this is a union of 2 events, the event of 3 happening and 6 happening. So it means that either this happens or that happens, or both will happen. Of course, we know in this case both can't happen, but this is what union means. At least one of these will happen. So we have a union of these 2 events. Okay, so you can represent events and outcomes with a Venn diagram. And this we will call the universe of events or outcomes. This contains everything that could happen in this experiment. We call it U, all possible outcomes. So let's take an example with the Venn diagram. Let's say that we have our universe of events here. And let's say we throw a die. So 1, 2, 3, 4, 5, 6. Okay, that's how now we want to represent the event X that the die is an even number. But the die, I mean, is the outcome of the die is an even number. So if I throw the die, this is the event that the die is an even number. And then we see that this corresponds to this event. So X, that's X. Okay, and let's take another event, that Y, that is the die is greater than 3. Means that the outcome of the die is greater than 3. Then we see that that corresponds to this event. So here we have y. Okay, what does this mean then? X, u, y. That's the union of the events x and y. That consists of all the outcomes that belongs to at least one of them. So this means that 2 will happen, or 4 will happen, or 5 or 6. So at least one of these will happen. Then we're also going to talk about the overlap, or rather the intersection. So this means the intersection of 2 events. So that means that both will happen. So this means and. So this symbol means or, and this means and. So x and y will happen. In what cases will both happen? That is if we throw a 4 or 6 on the die. So in this case, we will have that both x and y will happen. So this means or, but now note that this is a logical or, meaning that at least one of them will happen. So it's not excluding or like in everyday speech, but it's a logical or, meaning that at least one of these will happen. So this means or this will happen, or that will happen, or both will happen. And this and means that just both of them will happen. So and. So this is logical or, and this is and. So both will happen if 4 or 6 will happen. So that's a union and intersection. So we can easily see with the Venn diagram the intersection and union. You see the union is a combination of these 2 events, the totality, while the intersection is the overlap of these 2. So it is this part here. So more generally, we have like this. So if you have all possible events here, u, and then we have some event x, and then we have some event y. Then this here, the overlap, that corresponds to the intersection. Okay, so that part here corresponds to x and y. So if you have an outcome in this area here, you will get the event x and y will happen. If we have an event as inside this totality, so you have the totality here of events. So these combinations here, that corresponds to the union of the 2 events. So that is x or y, x union y. So that means that x will happen, or y will happen, or both will happen. Then this event will happen. So for example, let's take another example. Let's say x, it rains. That's one event. Or y is the die is even. So we represent these 2 events. X it rains, y it's even. Then this means that if at least one of these will happen, then we know this will happen. So if it rains, or the die is even, or both happen, then we know that this will happen, per definition. So that's the meaning of x union y. And x intersection y, that means both will happen. So that it both rains and the die was even. So this means x or y. But now there's, in everyday language, this or means and or. So it's a logical or. At least one of them will happen. And this means x and y. So that's the meaning of this union intersection. And we can represent this sometimes with the Venn diagram, because it can be useful. Let's now look at something called the addition rule of probability theory. And what is addition rule? It is the following formula. It says that x, the probability for x or y to happen, that is given by the probability for x plus probability for y minus the probability for both to happen. So this is called addition rule. So the probability for an event to happen or another event to happen, that is x or y to happen, then we add a probability for them separately, but we'll have to take away the overlap. So this is rule that holds for no matter what x and y is. For example, what's the probability of getting a die is even and the die is 5 over 6? Then we could calculate it using this formula. So let's take an example here, concrete example. We'll soon show this formula, how you can show it. Well, let's say that you throw a red and a blue die. Okay, so we throw a red and a blue die. Okay, so we have thrown a red and blue die. What is the probability that at least one of the die show a 1? So what is the probability that at least one die show 1? Okay, so then we have to make some events here. So x will be, we will write as the red is a 1. So I will just write a shorthand. So this means that the red die shows a 1. And then the event x is that the blue die show a 1. So this shorthand means just blue die shows a 1, and this means red die shows a 1. So you don't have to write as much. Okay, now we want to find out what is the probability that the red die will show 1, or that the blue one will show a 1. That is meaning of at least 1. So this means at least one of the die show a 1. Then according to addition rule, this is the probability that the red will show 1 plus the probability that the blue will show a 1 minus the probability that both of them will show a 1. Okay, so what's the probability for that? The probability that the red die shows a 1, that's 1 chance in 6, of course. Every side is as likely to have one side in 6 for this. What's the probability that we'll have a blue 1? There's also 1 in 6. But then we have to take away the probability for that both of them show a 1. So what's the probability that both of them show 1? Okay, if we throw 2 dice, then the blue die could show 1, 2, 3, 4, 5, 6. And also the red die could show 1, 2, 3, 4, 5, or 6. Then we can make this table here. So we divide up into 6 columns and 6 rows. So this means that, for example, this square here, that corresponds to that the red die showed a 3 and the blue die showed a 2. And for example, that's the one down here in the corner, that both dice show a 6. Okay, then we want to find what does this correspond to, that both dice show a 1. That is this square here. This square, for that to happen, that is just as likely as any other square to happen. So this outcome is just as likely as any other. Now, how many squares are there? 6 times 6, 36. So the chance of that happening is 1 in 36. So that both dice show 1 is 1 in 36. And then we know everything we need to know. 1/6, then we need to subtract 1/36. So this is 6/36 plus 6/36 minus 1/36. So this is 11/36. So the probability is 11/36. If we would have 12/36, that would be exactly 1/3. So 11/36 is a little bit smaller than 1/3. So this is roughly 31%. So we cannot just add. We cannot just add a probability that we get the 1 on the one die and 1 on the other die. Just adding these two would give 2 6 as a 1/3. 1/3 is 33%. But actually the probability is a little bit smaller than that, because we have to take away the overlap. So we have to take away the overlap or the intersection. So the probability that at least one will happen is 31%. Okay, so that's how you can use this rule here. Now we want to show where does this rule come from, because some may think that this here seems strange that we should have this part. Some think that we just could add the two probabilities, but we need to have this one also. And now we will give a proof of this. Okay, now we skip about the red and blue die. Now we just look at the general situation. So let's say we have now a Venn diagram, because we will see that it's useful to draw a Venn diagram. Okay, so we have here, this corresponds to X, and this corresponds to Y. And then the intersection or the overlap here, that is X. And let me draw it like this. So that's the intersection. So that's X and Y. And the union, of course, is the total colored area here. So if we end up anywhere here, then that's the union of X or Y. So the totality here, that's X union Y. Okay. Per definition, if we repeat an experiment, if now, for example, X and Y have to do with die or whatever, it's some experiment we can repeat, then per definition, f of X, that means so many outcomes that for which X is true. For example, if X correspond to the die is even, this is so many outcomes that gave that X was even. So this is how many times X will happen, or X will be true. So this is number of outcomes in X. So we will have an outcome. Sometimes we have an outcome there, and sometimes we have an outcome here, sometimes we have an outcome here. So this means as that many times that the outcome ended up somewhere in x. In the same way, this means for y. How many times we ended up with an outcome in y. So that's just per definition what it means with the symbols. And this is how many outcomes that happened in, or that was in x intersection y. So sometimes you have an outcome here, sometimes you have an outcome here, here. But here, in the overlap intersection, this is how many times we ended up there. And this is, per definition, how many times we ended up in the union, in anywhere on this colored part. If we didn't end up there, we must end up outside it. Okay, so these are just the definitions, what is f of x, f of y, and what all those mean. You can see from the Venn diagram that if we take x union y, how many times did it end up in here? Then this just to add the number it went up in x. So how many times did it end up in here? Then just so many times it happened up in x, plus so many times it ended up in y. But then we see we have calculated now this part 2 times, because it belongs both to x and y. So if you just take the number of times we end up here, plus the number of times we end up here, we count this twice. So you have to take away those times you calculated this once. So if you take away that once, they will be corrected for having calculated it twice. And how many times have we got an outcome here? As per definition is this. Okay, so just for frequency we have this. Let us now divide both sides by the number of times we repeat the experiment. Okay. Now a rule for division is that we can divide each of these. That's f of x divided by n plus f of y divided by n minus f of x overlap y intersection. Okay, we have this. If we now repeat this experiment millions and millions of times in an ideal limit infinite many times, what is this here? This is just the relative frequency. Written here is just a relative frequency. And we know that relative frequency will be equal to a probability if we have repeated it many, many times. So what's written here is just the probability for x union y in the limit that we have repeated this infinite many times. This here, in the same way, if we repeat it infinite many times, this is the, or no matter if we repeat it or not infinite many times, this is the relative frequency. But the relative frequency is equal to the probability if we have repeated it infinite many times. So that one is the probability for x. And this will be the probability for y. And if we repeat it infinite many times, this will be the probability for x and y. But this is just the addition rule. So in this way we have proved the addition rule. Okay, so this is a proof of that. So we see that the reason we cannot just add the probabilities, it's tempting to say just add probabilities. For example, what is the probability we get a 1 or a 2 on the die? We can't just add the probability for getting 1 and 2. We have to take away the probability that both will happen also. Because this here comes from the fact that otherwise we have calculated this area twice. If you just add a probability, we will calculate this part twice. Therefore we have to take it away once to correct for that. However, there are some situations where we have special cases where we can just add the probabilities. So let's say that we have two events looking like this, or schematically looking like that. So we have our Venn diagram. So this is x and y, but intersection, there is no intersection. The overlap is 0. They don't overlap. That means that if x happens, y cannot happen, and vice versa. In this case, if we have this formula, the addition formula, we know that it's always equal to this. But this last term here means that both will happen. But we see that since they don't overlap, this cannot happen. So this probability is 0. So if it looks like this, special case, then we can just add the probabilities. So we do have this situation, we just add them, but it is only a special case when they don't overlap. If they do overlap, we have to take this into consideration. So let's take an example of this. Let's say that x is a 1. That is, if we throw a die, we get a 1. And y is the event that we get 2 on the die. Okay, what is then the probability for x or x or y to happen? Yeah, that means that 1 or 2 will happen. Okay, according to this addition rule now, we can write this as probability for 1 to happen plus probability for 2 to happen minus the probability for both to happen. But both cannot happen. You cannot have both 1 and 2 on the die. So we know that this is 0. So in this case, you can just add the probabilities. So this is 1/6 plus 1/6. So this is 1/3. So there are special cases when the events cannot happen at the same time that you can just add the probabilities. But that's a special case. In general, you need to keep this here. Okay, so let us take another example. Let's say that x is, we have 1 or 2 on the die, and y is 2 or 3 or 6 on the die. Okay, what is now the probability that at least one of them will happen? Then again, this addition rule gives us this. The probability for x to happen, 1 or 2, that's just 1/3. That's just what we saw. So this is just 1/3. You can just add the probabilities in this case. 1/6 for this, 1/6 for this, since both of them can happen. And also here, these cannot happen at the same time. So it's just to add 1/6 plus 1/6 plus 1/6, that's 1/2. But what does x and y correspond to? It means that 2 happens. If 2 happens, both of them happens. So this corresponds to 2. And the chance of that happening is a 6. So this is probably 1 in 6. So now this is 2/6 plus 3/6 minus 1/6. So this is 4/6, or 2/3 if you like. And this is roughly 67%. So the probability for at least one of these to happen is 67%. So in this case, we need to have this included, otherwise it will turn out to be wrong. The next thing we will look at is conditional probabilities. And conditional probability means that a probability for something to happen is conditional on something else to happen. For example, what is the probability for it rains in 10 minutes from now? So what's the probability of that? That is dependent if we know that it's cloudy or not. So what is the probability for it to rain in 10 minutes? Let's say that we know that it's cloudy. So we know that it's cloudy. And we know that it's given that we write in probability as a vertical line like this. So this is the probability for it to rain in 10 minutes if we know. So after this line we know. If we know it is cloudy. Which of these probabilities are larger? Yeah, common sense says that this probability is larger, because if we know it's cloudy, then probability for it to rain is larger than if we don't know anything about the weather. Or take another example. What's the probability of getting, for example, what's the probability of getting ace of spades, ace heart? What is the probability of getting that? Let's say we draw a card from a deck. What's the probability of getting ace of hearts? And on the other hand, what is the probability of getting ace of hearts, given that we know that we have drawn a heart? Okay, so in the first case, we want to find out the probability for drawing a card from a deck and drawing ace of hearts. In the second case, we have the same situation, but we know that we have drawn a heart, but you just don't know if it's an ace or something else. But if you know the drawn hearts, then the probability is larger that it will be ace of hearts than if we don't know anything about what we have drawn. So this probability is larger than that. So you see, probabilities depend on what we know. So here we don't know anything, and here we know this. So this is called a conditional probabilities. This is called a conditional probability, and this is a conditional probability because they are conditioned on this. More in general, we say that the probability for X to happen conditioned on Y has happened. So this is the probability for X to happen, given that we know that Y is true. Yes, probability for X to happen, given that Y is true. Then, having introduced conditional probabilities, we can talk about dependent and independent events. X and Y are dependent events. This is the definition now of dependent events. So what do we mean by X and Y are dependent events? Yeah, that is if the probability for X is not the same as the probability for X, given that we know that Y has happened. So if these two probabilities are not the same, then we know that X and Y are dependent events. That's the definition of dependent events. So if this holds, if these two probabilities are different, then we say that X and Y are dependent. And here we could just as well have like this. So if probability for Y is not the same as the probability for Y if we know that X has happened, not equal to, then we say that they are dependent events. So that's the definition of dependent events. And similarly, we define X and Y are independent events. If the probabilities are equal. So if the probability for X is equal to probability for X, given that we know that Y has happened. So here these two probabilities are the same. So it means that the probability for X is the same as the probability for x given that y has happened. It means that it doesn't matter if we know that y has happened or not, because the probability won't change. So these two events are independent. We can also write it like this also, this condition, as probability for y given x. So if either of these has happened, or if either of these are the case, then we know that events are dependent or independent. So that's the definition of dependent and independent. So independent if it doesn't matter if we know y, because it doesn't change the probability for x anyway. But here it changes the probability if we know y, we do not know y. Having defined conditional probabilities, we can now write the multiplication rule of probability theory. And that is that the probability for x and y, so the probability for both, is given by, according to multiplication rule, probability for one of them, probability for x, times the probability for the other one, given that the first one has happened. And we can just as well write it also like this. It doesn't matter if we take p of y here first, and then that is exchange the roles of these two. So both of these are called a multiplication rule. So the probability for x and y happen is probability for one of them times probability for the other one, given that the first one has happened. So this is the multiplication rule. So let's take an example. What is the probability for getting, if we draw a deck from a card, what is the probability for getting a heart and an ace? We draw one card from a deck. What is probability that card is a heart and that is an ace? Of course, this is the same thing as the card is an ace of hearts. And what's the probability for that? You have 52 cards in the deck, so the probability is 1 in 52 for that, of course. But we can also calculate this using the multiplication rule. This is the probability for having a hearts times the probability for having an ace, given that the card was a heart. Okay, what's the probability of getting a heart if you draw a deck from a card? That's 1 in 4, because of 4 suits, and each suit is equally likely. And what's the probability of getting an ace if you know the card is an ace, is a heart? Yeah, that's 1 in 13, because in every suit there are 13 cards. So this is the probability for getting 1/13 is probability for getting an ace if you know it's heart. Then we have to multiply these two, and this is of course 4 times 13, that's 52. So you see that we get the same answer. So if we just reason directly or we use the multiplication rule, we will get the same answer. So this is some motivation for why it works, at least, and an example how it works. But let us now prove that it works always. Okay, let us draw a Venn diagram for support for our thinking. So here we have x, and here we have y, and here we have the overlap, x and y. Okay, let us start with the concrete case and then we generalize it. So assume that you repeat an experiment 1,000 times. So let's say that you are repeating an experiment 1,000 times. So n is equal to 1,000. And let's say that you have gotten 100 outcomes in y. Okay, so you have gotten 100 outcomes in y. And you have gotten 30 outcomes in the overlap. So if you repeat 1,000 times, let's assume that you have gotten 100 in y and 30 in this overlap. So of the 100 has ended up here, 30 of those has ended up here. So of those 100 in y, 30 of those has ended up in the overlap. That means that the probability for ending up in x, so the probability for ending up in x, given that we know that the outcome is in y, or ended up somewhere in y, that probability is 30 divided by 100. Because 30 divided by 100, that's if we know that it has ended up in y, then we know that the probability it has also ended up in x is 30 divided by 100. So this is the probability that it has ended up in x if we know it has ended up in y, just based on this data here. Okay. In this situation we have that 30, that's equal to f of x. And y. You see here, there is a number of the frequency of this event. So 30 is equal to this, according to the written here. And 100 is the frequency of y. How many has ended up in y? Okay, so we have the probability for this is equal to this. Okay, so we have this. Now we know from before that what is the probability of an event. Let's not call it x because not confuse with x here. What is the probability of an event? That's the frequency of that event divided by n. Okay, and this we can rewrite as f of a is equal to n times the probability for a. So let's use that here. So we see that f of x and the y, now x and y corresponds to a here. Then we just take n times the probability for this event. So you see that f of x and y is n times p of x and y, according to this here. And the same in the denominator. Take n times p of y. That's equal to f of y, according to this. And now we see that we can shorten out this. And then we're left with this part. So this is equal to that. But this is just the multiplication rule. Let's say now we multiply both sides with py. So we multiply this by py. And it's equal to that. But what is written here is nothing else than the multiplication rule. So this is just the multiplication rule we have proved now. And to get the other version of the multiplication rule, we have changed the rules x and y. We just have to change the rules here and reason exactly the same way. So this is proof of the multiplication rule. Let's just say now that we have a special case where we have two events that we have this situation. If we have the special case of independent events, so that then the multiplication rule will simplify a little bit. So if you have x and y, and according to the multiplication rule, we have this. But if we know now that x and y are independent events, then this part is just p of y, because it doesn't matter on x. So independent events, these two probabilities are the same. So in this case, we can just write this as this. So this multiplication rule simplifies to this if the events are independent. So if the two events are independent, we can just multiply them separately, the probabilities for the two events separately. For example, if x is getting if we have thrown a dice twice, or let's take a die instead. We're throwing a die. Let's get a 5 on a die, and the event is getting an ace of hearts when we draw a card from a deck. These two events has nothing to do with each other. So if we know that we have gotten a 5 on the die, it doesn't change anything about drawing a card and vice versa. So the probability of getting a 5 with the die and getting ace of hearts, if we draw a card from the deck, these are independent events. So in this case, we can just multiply them, the probabilities for the two events. Of course, this probability is conditional probability. For the probability of getting this, for example, given that we know this, it doesn't matter because they are independent events. So in this case, we just can multiply the probabilities. So this is 1/6. We're getting a 5 on the die, it's 1/6. We're getting an ace of heart, is 1 in 52. So in this case, it's just 6 times 50 is 300. So 312. So in this case, we can just multiply the probabilities. But in general, we cannot do like this if the events are dependent. So if the events are dependent, we cannot just do like this. We have to take into consideration that they are dependent. What is a complementary event? If we have an event x, let's denote the complementary event with the bar over it. So this means that x will not happen. So per definition means not x. So if x do not happen, so that's the opposite of x. We can draw a Venn diagram. For example, if I have the event x here and the universe of events here, then the complement is everything that's remaining. So that means that we end up outside x. So this is x complementary event. So for example, if x is equal to, you have a 2 or a 3 on the die, then not x is equal to have a 1 or a 4 or 5 or 6 on the die. So together they make up the whole complete what could happen. So we know that one of these will always happen, but two of them will never happen at the same time. So these are complementary events. So if you have two events, a complementary x and x complementary event, we know that one of these will always happen. So the probability for them, the sum of them is 100% or 1. So one of them must always happen. And then we can write out like this. We can rewrite this formula as the probability for an event to happen is 1 minus the probability for the complementary event to happen. Just rewriting this expression, this equation. So we can always calculate the probability of an event as 1 minus the probability for the complementary event to happen. And sometimes it can be easier to calculate the complementary event than the event itself. So in this case, that can be useful to use this rule. Let's take an example. We saw before that what is the probability of getting at least 1 1 on 2 die. We had a red die and a blue die. And what was the probability of getting 1 on at least one of the die? Then we saw that that was 11/36. Okay, so the probability of getting at least 1 on 2 die. And then we used addition. To come to that conclusion, we used the addition rule. Okay, but we can also use complementary events to figure that out. So the probability of getting at least 1 on 2 dice. So that is, if you throw 2 dice, for example, a red and a blue one, it doesn't matter the color really, but at least getting at least 1 on a die. What is the probability for that? We saw that was 11/36. But we can also calculate this as the opposite. 1 minus the opposite of that, the complementary event of that. And what is the opposite of getting at least 1 on 2 dice? That means that getting no 1 on 2 dice. Okay, so this here is the complementary event of that one. So getting at least 1 on a die, on 2 dice, that is complementary of that is getting no 1 on 2 die. And what is the probability of getting no 1 on 2 die? If we throw a die twice, what is the probability of getting no 1? On the first die is 5/6 to get no 1 on 2 die. And also on the second die, 5/6. So this is just a multiplication rule. So getting no 1 on 2 dice means we got something else than 1. And probability of getting something else than 1 on the first die is 5/6. And then we need to multiply with the probability of getting something else than 1 on the second die. That's also 5/6. So this is the probability. And this is 25/36. And if you take 1 minus that, that is 11/36. And that is just what we are right here. So in this case, we can use complementary event to calculate also. So if you find that easier. In this case, it was the same difficulty, these two. But for example, if you instead throw 4 or 5 or 6 dice, then it will be tricky to calculate this using this. And then it will be much easier to calculate with using complementary events. So using complementary events can sometimes simplify your calculations a lot. Up to now, we are used quite freely, without talking about it, uniform probability distributions. And what does that mean? That means that the probability for every outcome is the same. If I throw a die, the probability for getting every outcome is the same. If I throw a normal coin, the probability of getting both heads and tails is the same. So if the probability for all outcomes is the same, then I talk about uniform probability distribution. So let's say I have 2 outcomes. What is the probability of getting one of those if it's uniform? It is of course a half. So if I throw a die, if I throw a coin, then getting heads is 1/2, since we have 2 outcomes and both of them are equally probable. That's a uniform probability distribution. If I throw a die, then the probability of getting any of the faces of the die is 1/6, since each side is equally probable. Or if I have a deck of cards, the probability of getting any card is 1/52. So we have a uniform probability distribution. We can always calculate the probability just by taking 1/n for any outcome. And we also have that, for example, let's say that we have a deck of cards. What is the probability of getting an ace? So what is probability of getting an ace in a deck of cards? Yeah, then we have 4 possibilities. There are 4 aces out of 52. So you can just calculate it like this, because you have 4 probabilities and all 4 chances, and all chances are equally likely to happen. So you have 4 52s with chance of happening. More generally, if we have a uniform probability distribution, we have, if this is the number of chances that it will happen, and this is the total number of outcomes there are. So these are the number of outcomes that will be beneficial for us. For example, the ace. And this is the total number of outcomes. We can calculate the probability like this. So special case is that. So this we can use if we have uniform probability distribution. So for example, getting an even number on the die. There are 3 possibilities of getting an even number. And you have to divide by 6. So that's just in half. So that's talking about uniform probability distribution. Up to now we have used this quite a lot already without talking about it, because it's almost common sense. So let us take an example again with having 2 dice. So if you have a red die and a blue die, but of course it doesn't matter the colors, but let's say we have 2 dice, and you want to find out what is the probability of getting at least 1 6. And that of course the same probability as getting at least 1 1, but it's easier to say 1 6 than 1 1. So let's say take this probability, at least 1 6 on 2 dice. That we have seen now in how we can calculate in different ways. So let's now go back to what we did before, was make a table. So we put here 1 2 3 4 5 6, and for the blue die 1 2 3 4 5 6. Then we see that, or we saw that we had 36 squares, 6 times 6 squares. And each of these squares was equally likely to get. For example, it's just likely to get a red 4 and blue 2. This as getting a red 2 and a blue 6. Which of these corresponds to getting at least 1 6? It is this here. So these squares means that we have gotten at least 1 6. Here we have got the 1 6, and this square we got the 2 6, and here we got the 1 6. And then each of these are equally likely. So we can just calculate what is the probability then. That is just the number of favorable outcomes. And these, we just count here, this 5 plus 5 plus this 1 in the corner, that's 11. So we have 11 favorable outcomes of total 36. And that's just the probability we had before. So this is an example of having a uniform probability distribution and calculating using this rule here. An outcome tree is a useful tool to calculate probabilities. And to explain what an outcome tree is, let's take a concrete example. Let's say we have a box of balls, and we want to draw randomly balls from there. So let's say that we have 3 green balls. So 3 green balls. and we have 7 blue balls. Okay, so we have a box or a bag or whatever with balls, and they are all identical. So if you just feel the balls, we can't tell if it's blue or green. So let's say now we draw randomly from this box of balls 2 balls. But you draw them one at a time, and after drawing the first one, you don't put it back when you draw the second one. So you draw 2 balls without replacement. So you draw one and then draw another one without putting back the first one. What is then the probability of drawing, for example, different colored balls? So what is the probability of drawing different colored balls? Okay, so different colored balls. We draw 2 balls without replacement. In practice, that means that we draw 2 balls at once at the same time, or we draw 2 balls one after each other, but without replacing, without putting back the first ball when we draw the second ball. So that's what it means to draw 2 balls without replacement. Okay, so now let us see how this can be calculated. And then we can use an outcome tree. For the first ball, we have 2 possibilities. Either the first ball is blue or is it green. So the first ball is blue or it is green. Let's say that we drew a blue ball on the first one. Then when we draw the second ball, we also have 2 possibilities. It can be blue or it can be green. So this means that we drew blue ball on the first one, then the second ball could be blue or green. And of course we have the same options here for the other part of the tree, the branch. So this is an outcome tree we're drawing. So here, if we draw a green on the first, then we can draw a green on the second or a blue on the second. Okay, so this is an outcome tree. So if we follow this branch, this shows all the possibilities we can have. So if this means that we got a blue and then we got a blue, so then we end up with 2 blue. And here means that we got a blue and then we got a green. So it means that we got a blue and then got a green. Here it means that we got a green and then got a blue. And the final part of the tree means that we have gotten a green and then we have gotten a green. So this shows all the possible outcomes we can have. Okay, so what's the probabilities of getting 2 different colored balls? That means that we have this situation. We drew a blue and a green, or a green or a blue. So we need to calculate the probability for this to happen. And to do that, we continue to fill in our outcome tree. What is the probability of getting a blue ball on the first? Yeah, there are 10 balls and 7 are blue. So 7/10. And then of course it's 3/10 to get a green on the first. Okay, so what's the probability of getting a blue on the second ball if you got a blue on the first? Okay, on the second ball we have assumed that we've gotten a blue here, a blue ball on the first. That means that when we draw the second, there is 1 blue less in the box. So now it's only 6 blue balls left of a total of 9. So 6/9 is the probability of drawing a blue ball on the second if you draw a blue ball on the first. And we have 3 green left of 9. So the probability of drawing a green on the second one, if you drew blue on the first one, is 3/9. Okay, similar here. If you drew a green on the first, then drawing a blue on the second, okay, there's 7 blue left of a total of 9. And here we have how many greens left? 2 greens left, since we removed 1 green of a total of 9. Okay, so then we need to see what is the probabilities of getting out here, because these are the probabilities we're interested in. 7 times out of 10 we get the blue in the first, and out of these cases, in 3 of 9 of the cases we get the green here. So for 7 out of 10 times we get a blue in the first one, and out of those times we get 3 times out of 9 we get the green on the second. So we need to multiply here. Similarly here, if we draw green on the first, that happens 3 times out of 10. And out of those times, 3 times over 10, it happens 7 times of 9 that we draw a blue on the second. So to go in this branch, we need to multiply the probabilities. And okay, so what this is 21 divided by 90. Of course we could simplify first, but and this is also 29 by 90. And then, so this is the probability of getting a blue green, and this is probability of getting a green blue, the same probability in this case. But now we're interested in either of these, so we need to add these two. Then somebody could ask, shouldn't we take the overlap also, minus that? Yeah, but these two cannot happen at the same time, so there is no overlap. So this is 4290, or 2145, or 7, you can divide by here, so it's 15. So the probability for getting different colored balls is 7 out of 15. 7/15. And that 7.5, 15 is 50%. So it's a little bit less than 50%. So almost in half of the situations we get different colored balls, but a little bit less than half. So we see here it is very useful to draw an outcome tree. So when we go in this direction, we should multiply the probabilities like this. And when we get the outcomes here, if we should combine events like this, then we need to add them. So you can intuitively think of adding in this direction, multiplying in this direction.